So for this class, we're going to look at the chain rule with multiple variables. So we've been studying functions of multiple variables. Now we want to start actually doing some calculus with them and being able to take some derivatives more than just partial derivatives, but actually nested functions as well. So let's go ahead and get started with that. So let's first recall the chain rule in one variable. So this is basically the chain rule was how we took a derivative of composition of functions. So supposing we have h of t is f of g of t. So we have h is the composition of f and g. Recall that when we took the derivative of this, we had the derivative of f with g of t still inside, and then we had to multiply that by the derivative of the function inside, so the derivative of g. Another way to write this, which is going to be a little bit more helpful for what we're going to do with multiple variables, is let's go ahead and let that inside function g of t be equal to s, so that we could write y is equal to f of s. And so then if we write the chain rule in this way, we take dy dt, this is dy ds is the derivative of f with respect to s there, and then we take the derivative of g with respect to t, so that's ds dt. So notice here, this, if we want to compare these above, this part here, the dy dt, is the same as h prime of t. dy ds is this term here, the f prime of g of t, and then ds dt is just g prime of t. So that form is going to be a little bit more helpful for going forward with more variables. So now let's consider the easiest setup for a chain rule with multiple variables. So we're going to start with a function of two variables like we've been looking at, f of xy. And suppose x is a function of just one variable t, and y is a function of just one variable t. So this is the easiest case we could have. And so in particular, if we replace the x with g of t and the y with h of t, we see that this function, this z is equal to f of xy, z here is really a function of t. So since z is a function of t, we could ask, if I change t, how does that change z? Which is the same thing as asking, what is dz dt? So what is the derivative of z with respect to t? Now, of course, we could just plug these functions in, and then we would just have z as exactly a function of t, and we could take that derivative. But we're going to use this to illustrate the chain rule, because it's the easiest case, and we can use it for good motivation. So let's consider the differentials. So delta z and delta t. We saw differentials in the last section, so we're going to use that information to help us with taking the chain rule here. So recall, we had that the delta z, the exact change in z, was approximately the dz, and we calculated that as the partial of z with respect to x dx plus the partial of z with respect to y dy. Now, if we go back to our one variable differentials, which we also reviewed last class, we could say delta x is approximately dx, and that's equal to dx dt delta t. So normally we have our function when we're doing differentials would be like f of x, and so then you'd have a df dx delta x. But in this case, we're considering x as a function of t. So the x here is taking the place of our f that we would normally have. And then similarly, y is also an independent variable, and it's a dependent variable upon t. So we can say delta y is dy, which is dy dt delta t. And so we can make these replacements into this equation up here, replace the dx and the dy here. And I'm going to get delta z is approximately these terms here. And so remember, since t is our independent variable here, dt is delta t. So I can divide both sides of this equation by delta t, and I'll get delta z over delta t is approximately delta z delta x dx dt plus delta z delta y dy dt. So now what we're going to do is we're going to take this equation here, and we'll let delta t go to 0. And if we do that, the left-hand side here becomes dz dt. So I have dz dt is delta z delta x, dx dt, delta z delta y, dy dt. And so that's our chain rule for a function here where we have two variables x and y, and each of those is a function of t. And we don't really want to memorize things if we don't have to, so let's go ahead and see how we can do this without trying to memorize this. So what we do is we draw a diagram here. So z is our outside most variable, and that depends upon x, and it depends upon y. So we draw these arrows down. We label the next level down x and y, and we draw the arrows from z to x and y, showing that z depends upon x and z depends upon y. And then similarly, x and y depend upon t, so we put a t down here and we draw these arrows. Now along these arrows, notice that since there's two variables in this row here, we're going to use partial derivatives. So going from here to here, we put the partial of z with respect to x, and here we put the partial of z with respect to y. Now going down in this direction, there's only one variable down here, so we use dx dt here and dy dt here. And so now to get the derivative of z with respect to t, we follow each path down. So we take this path and then this path. So that means we take this times this, and then we add it to this path here, going here and here. So we can see, for instance, going down this path gives us this term here. Going down this path gives us this term here. And it might seem like this is a little bit more complicated, and why not just memorize it? It's not that complicated of a formula. But we're going to see, we're going to have cases where there's going to be lots more variables, and maybe x and y depend upon more than one variable as well. And these diagrams will be very helpful for figuring out the formulas for chain rule rather than just trying to memorize every possible situation. But before we go on to any more complicated situations, let's go ahead and look at an example. So let's suppose z is equal to f of xy, which is x times sine y. And then we're going to have x and y both be functions of t. So x will be t squared, y will be 2t plus 1. And now we just calculate all those derivatives we needed. So the partial of z with respect to x, partial of z with respect to y, and then dx dt and dy dt. So those are all pretty easy to calculate. We're going to go ahead and plug in 2t plus 1 for y and t squared for x to get these equations here. And now we just use our formula. This is dz dt is dx dt dz delta z delta t for this term, and similarly for dy dt delta z delta y gives us this term. So pretty easy. We're just taking derivatives and partial derivatives here once we understand how to use the diagram to get the equation. So now let's go ahead and consider the more general chain rule. So we see how we can go to more variables. And then once we do this a little bit more generally, it'll be easy to generalize to any number of variables. So we're going to draw these diagrams to help with this. So now let's suppose we're not going to go super complicated. We're just going to add one more variable. So z is still a function of x and y, but now I'm going to let my x be a function of two variables. So x is a function of u and v, and y is a function of u and v. So let's draw our diagram that goes with this. So z is a function of x and y, so we put those on the row here. And then x and y are both functions of u and v, so the next row has u and v in it. And then we draw all these arrows and label them just like before. So going from the top row to the second row, there's two terms in the second row. That means we use partial derivatives. And now the difference is going from the second to the third row. Now there's two variables down here, so we need partial derivatives there as well. So I go delta x, delta u here, and then go from x to v here, I use delta x, delta v. And similarly for the y's. And so now, if I want the partial derivative of z with respect to u, I'm going to go all the paths I can to get to u. So I'm going to go down through x, so that gives me delta z, delta x, delta u, and then I've got to go to u in another direction, so I'm going to go from z to y, and then y to u, and that gives this term here. And similarly for v, you're going to go down these paths here to get to v. So you can see this is a very nice way to do this, because we're just drawing diagrams here and then labeling the diagrams. And no matter how many variables we get or how many levels we get to this, we could add more variables inside as well. So u could also be, u and v could be functions of s and t, for instance, or so on and so forth. We can just continue down these diagrams and get the chain rule each time without having to memorize anything other than how the diagram works. So let's try one more example with more variables here. So let's let z be x times e to the y. Let's let x be u squared plus v squared, and y be u squared minus v squared. So if I want the partial derivative of z with respect to u, I calculate delta z delta x, which is just going to be e of y, and similarly delta z delta y. And then I need to go from x to u, and so that's just going to give me a 2u, and from y to u, which also gives 2u, and then we just multiply these together to get our partial derivative here of z with respect to u. So that's it for the chain rule and multiple variables. We'll see more examples of this, but understanding the diagrams is really the important part here. If you can understand the diagrams, you don't have to memorize much of anything, and then it's just a matter of taking derivatives and partial derivatives.